How is everybody today? Very good. Okay, so we're going to go into lab number 3 in Organic Chemistry 1, and today we're going to learn another technique that are very, very important for the identification of any chemical, any compound. So in the handbook, like physics and chemistry handbook, usually you will see the list of all the chemicals, and the most important part, which are some of the physical property, are the boiling point and the melting point has to be listed. So if we are going to have a liquid, then we are going to list the boiling point. If we have a solid, then they're going to put the melting point. So we need to know something about the boiling point and melting point, how it is going to be determined. We have so many different techniques. We're going to learn into the techniques, but behind that, how is the temperature going to reach the boiling point? So you can see here, boiling point is the temperature at which the liquid is going to be transferred from the liquid phase into the vapor, or like the gas phase. This is how we are going to change from one to the other, okay? From one phase to the other. Now, how is it going to reach that point? At the point of the boiling, we see that the pressure, because there is a relation between the pressure and the boiling point, and we know that the boiling point, for instance, of the water on the high, like upper altitude, will be different from the one on the sea level, right? They are not going to be the same. So how is it going to be changed? It's the temperature when it is going to reach the boiling point. The pressure on the liquid, on top of the liquid, has to be equal to the applied meaning the outside pressure. So the pressure on top of the liquid, the pressure on top of the liquid should be equal to the applied pressure, which is the outside pressure. Then we're going to reach the boiling point. So this diagram, you see that some of the phases are still we have on the top, sometimes we have a solid goes into liquid and then goes into a vapor. So this is we are going to have a triple, and this is the triple point, which is going to have a combination of those 3 phases in one. This is called a phase diagram, right? I'm sure we remember that somewhere sometime. But then what we are going to see that the temperature, as we are increasing the temperature, we're going to get into the the triple when we are going to have those 3. And then after you pass increasing the temperature, you're going to get into the vapor. In other words, when we're going to start boiling. Starting boiling from the minus with a specific temperature, with a specific pressure, at pressure of 1 atm, which is going to be 760. This is the normal temperature. We call it the normal temperature, okay, or boiling temperature. And then the temperature at 100 degrees, okay, Celsius. So this is how we are going to reach the boiling point. All right, beyond that, we're going to go into they call it supercritical. It is going to be beyond the 100, and even the pressure is going to be higher than 1 atm and more than 7, 60. It's going to be beyond that. So this is called the supercritical point. So this is how we are going to understand a list of chemicals where we are going to have some of these theoretically, which is a comparison between the boiling point and the functional group. But these are the 4 that you are going to have. If you are going to have another one, which is going to be the cyclohexanone, you can always do that. If we have time, we can always do that. So we have 5 of them. I do have these 5 liquid, which are basically, these are the organic compounds. So another 5 is going to be the hexanone. And the hexanone is acetone. Cyclohexanal is the aldehyde. Benzaldehyde, definitely it has the aromatic ring and it is an aldehyde functional group. Cyclohexane is just the, the structure. So if I give you the hexane, CH3, CH2, 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 CH3. We have 1, 2, 3, 4, 5, 6 carbon atom. This is a straight line, we call it aliphatic, and it is open. It's open, it's not cyclic. Cyclohexane is also aliphatic, but doesn't have any aromatic, in other words, no double bond. This is cyclohexane. Cyclohexane, that's the second one. Third one is cyclohexanal. Cyclohexanal is going to be C double bond OH, okay? Now, when we go into benzaldehyde, you see the differences? Then this is C double bond OH. This has no double bond, it's not aromatic. This is aliphatic cyclic compound, this is aromatic compound. And the last one is cyclohexanone, when you are going to have double bond O. That's cyclohexanone. Okay? So these are the structure. You can always make a comparison when we are going to measure the boiling point, right? So we see how is these different functional group, because we have ketone, we have aldehyde, we have aromatic, we have cyclic, we have open chain, aliphatic. So these are different structure, right? And usually you can always do that if we don't have time. You can always search about the melting or boiling point, and then see how it is going to affect the level of the boiling point. What we learned theoretically, can anybody tell me how is it going to affect the boiling and melting point with a functional group? In other words, do you know that this is 6 carbon atom and this 6 are carbon atom, right? 1, 2, 3, 4, 5, 6. And this is 1, 2, 3, 4, 5, 6. Which one of those two is going to have the highest boiling point? Based on what? How are we going to predict? Prediction. Just without even looking at the boiling point, we can predict which one is going to have the highest, according to what we learned.
Double bond.
Sorry?
Double bond. The one with that.
This has carbonyl group. The carbonyl group with electron, right? This is a heteroatom. Well, oxygen is a heteroatom. Comparing is only carbon and hydrogen, right? So this is, remember the intermolecular forces? According to the intermolecular forces. And when we are going to have a dipole, this is a dipole, right? Dipole, dipole. Plus van der Waals, because we do have these, CH2, CH2, CH2. So we have two kind of intermolecular forces that it is going to affect the boiling point. And that's how we are going to predict our boiling point and melting point, according to the functional group. When we have this, that it has double bond here, which is going to go through a rearrangement, in other words, resonance, and here we're going to have alternated double bond that it goes through resonance. We're going to expect that to be more, has a higher boiling point compared to this one. Both of them has the same exact functional group, but this has extra with the double bond, right? So it's going to be more polar comparing to that, and so on and so forth. And here we have a cyclic comparing to this cyclic. Again, this is having a heteroatom that it is going to be more electronegative comparing to the other. In other words, the dipole or polarity of this guy, which is cyclohexanone, is going to be higher than this, and therefore boiling point of this compound is going to be higher than that. So we're going to base our comparison according to the functional group, according to the structure, right? We're going to predict which one is going to be higher than the other. So this is what we are doing. On top of identifying. We are also identifying, if we're gonna have an unknown, we're gonna give you an unknown, and we will ask you to calculate, or, sorry, to measure the boiling point or the melting point. So according to the measured boiling point or melting point, we will be able to identify our unknown. So this is also another property that we will be able to use in like the measurement of boiling or melting point. So on top of that, we will be able to predict, like, also how it is going to affect the boiling point when we're going to have different functional groups. So this applies to both, all right? So you can have any one of those, or you can have both of them, or all of them, or just 4 of them if you have a chance. And then you're going to measure the boiling point. I will show you the technique and the setup of the apparatus after I talk about the melting point. Now the melting point is the point at which the solid is going to turn into a liquid. This is again the diagram when we're going to have a mixture. Because now we're going to have an unknown that it has a mixture with more than one compound. Usually the technique is like that. We take those, like whatever we have a list of these, like for instance, we have a list of these chemicals, all right? We're going to take each one of them by itself, okay? Pure, considerably it is impure, and we're gonna measure the melting point of that solid, okay? We know what it is, yes, because it's labeled and it has the CAS number and everything. Then we will be given a mixture of the unknown. So the mixture of the unknown, we don't know how many % of the mixture of each one of those two, right? Could be 50-50, could be 80-20, could be 60-40, any one of those. This is what you are going to observe. When we are going to have a pure, you're going to have a very sharp melting point, okay? Very sharp. It goes like this. You see, this is the temperature at A, which is 100% A. It's 100%. This is molar percent, okay? 100% of the A, like, chemicals. Then we have the B chemicals at this time, like here. Also, it's very sharp, and the range is not going to be that long, okay? Because when we have more than one, or what we call it impurity, then we are going to have a whole, like in a long range between the solid and the liquid when it is going to melt all of it. But then when we are going to have this kind of mixture at the beginning, we have 100% of the A chemicals, 0% of the B chemicals, as we are going to go through. And then we're going to see with the time, and by the way, this is going to take longer process, and we're going to prepare a different percentage of the mixture. But this is how we are going to, observe it. When you're going to have, let's say, 80% of A chemical and 20% of the B chemical, you're going to see the melting point of both of them, of the B and A, is going to be very low. It's going to be lower than the usual pure chemicals, okay? If we have 50-50, we're going to have it over here, something like that, okay? But it is going to be less than the usual, than the normal, when it is going to be a pure. So the purpose of that we are going to measure them when they are going to be pure, versus it is going to be measured when they are a mixture. Let's say we prepared a mixture 50-50, and we're going to compare between the pure melting point and when it is going to have the mixture. So this is another study that is going to help us know whether our chemicals are pure or contaminated. Now we know very well, like if I'm going to give you those and it is labeled, every single one of us will be able to search and find the melting point, right? So we already have these melting points. We already have the boiling point of those chemicals, right? So we will be able to return to the reference. we will be able to return to the reference, and we will be able to find how many percent went down, or how is the range went through. So that's another like study to help us know whether our chemicals are pure or whether they are contaminated. And it happens, by the way, it happens. Now, with a melting point, probably sometime we're going to face with some problems. For instance, if we are going to have a very, very or low melting point, sometime the melting goes beyond, like in other words, lower than what we expected, and then it is going to vanish altogether. It's going to go, like, you know, it is going to be disappeared. Maybe it is going to be evaporated if it is a short and small chemicals. When we are going to have a very, very huge compound and it has a higher melting point, sometimes it is not going to, it's going to go beyond what we expect. So these are some of the obstacles that we might face when we are going to measure those. So you have to be very careful, you have to observe it and make sure that you still have the chemicals, right? So this is what we are going to address today. As for the apparatus that we are going to use for the boiling point and the melting point, I will move to these apparatus. Mineral oil. Mineral oil boiling point is very high, higher than any of those chemicals that we are going to use, liquids, all right? So as you can see here, I can show it to you. What we have this Pyrex test tube, small test tube, and inside the test tube, I put one of those capillary tube upside down, okay? So then I'm going to insert it, like insert it here, the tube, and then hold it, make sure it is held properly. And then over here, if you look at the thermometer, number one should not hold, like, you know, touch the inner wall of that test tube, and it is going to go all the way about 1 centimeter above of your liquid. The liquid is going to be between 0.5 to 0.3 of the cc of the mil. You're going to put it inside this whole, like, Pyrex test tube, and then you're going to put the capillary tube. In other words, this is the tube, capillary tube over here. Put it upside down. Put it upside down here. And then you're going to hold it. The thermometer has to be inside because we want to measure the boiling point, right? The reason why we're putting this upside down, because when it is going to be boiled, you see it is going to go inside the capillary tube. And capillary tube should be, the heads, like the open is down and the lock, like, you know, closed in the top. So then you're going to see, how are we going to observe? You're going to see the minute it is going to start boiling, that's when you're going to record your boiling point, and you're going to see the liquid will go inside the capillary tube, the small tube, okay? And that's when we reach the boiling point. So this is how we are going to measure the boiling point. I didn't want, although I was reading the book and showing you, like, you know, in the Technique 7, showing you that this test tube will be directly on top of the hot plate. I mean, we can do that, but I don't want to have any splash or any, like, you know, inconvenience with the like procedure. Therefore, it is much, much safer to use a very, very heavy paraffin oil, mineral oil, and then when it is going to heat, it is going to heat the organic liquid. Okay, so this is how we are going to set up our own apparatus. For the boiling point, you can use one, like, you know, each one at a time. It's up to you if you want to decide, like, if you have, like, you know, 4. So you're going to use 4 of them. When it is, like, pure, then you're going to mix any 2 and see how the boiling point is going to change. So that is a very good exercise and, like, you know, maybe a comparison that we are going to be able to address today. The other one, which is the melting point. We have this melting point apparatus. You have the reading here. Just follow the reading. Follow the reading. It's very, very clear and stepwise. So first we're going to have it opened here. Like, this is on and off. But before you open it, you have to set it up, read the instruction, and then set it up on the level of the melting point. It has to, the highest melting point that we are expecting. How are we going to know that? Because we already studied, the list of the chemicals that we are going to have. We know what are the expected melting point. So we will set it up on the highest melting point, and then we'll take it from there. Usually what we do in this case, I have this watch glass, all right? And I'm going to put some of the powder inside this watch glass. And then I take the capillary tube, and then I'm going to start pack it with this chemical. It's very, very simple. And then what I do, I tap it, and it goes here about 1 milli, 1 to 2 milli height. You don't want to have it too high. In other words, you don't pack it with a huge amount, more than 1 or 2 milli of the powder. And then we are going to insert it here. There are 2 compartments. In other words, you can prepare 2 capillary tube and read it at a time. One time you can have 2. You can have the same chemicals. You can have 2 different chemicals. So after you pack it, tap it, and then you're going to insert it over there. And then you're going to look through, and you're going to watch. Now, we know what we are having, right? We know what is the expected melting point. You have to be careful. You don't want to miss it, all right? So, and this here, the digital screen is going to show you the melting point, okay? Graduating, or how it is going to increase. So we know in advance what are the melting point of those chemicals and what do we expect here in life, in person. So this is what we're going to do with the melting point. Now, in organic or any chemical reaction that we are going to prepare a chemical, we need the first thing, after we extract it, purify it, dry the powder, then we want to measure the melting point. When you are going to prepare a new compound, the first thing you're going to do after you dry it, you're going to measure the melting point, and then from the melting point, we'll take it to the spectroscopy to make sure that we are, yes, prepare what is required. Now, the melting point will take us to the, to the reference and tell us approximately whatever you prepared, and this is the correct melting point, and then we'll take it for further analysis. So this is what we're going to do today. Okay? Do you have any question for me? All right, now I want you to have this set up the same way. So we do have all the apparatus over there. We do have the hot plate. We do have the mineral oil and the beaker. I put for every single table, you do have all these glassware that you're going to need for your experiment today. All right? Thank you.